Okay, we're ready to go.
Okay. So good morning, everyone, and welcome to the 11:15 briefing on Wednesday, June 3rd, last day of the conference. This briefing will be on mysteries of the Milky Way. So, my name is Susanna Kohler. I'm the editor of AAS Nova, and I am here with my co-host, Rick Feinberg, the AAS press officer, and Tharni Kunchadi, the AAS Media Fellow, who will be monitoring the Q&A and helping with any technical issues that come up. For today's briefing, we've got a couple of press releases going out today, 2 of them, and then the other 2 presentations are discussed in the press release that went out on Monday. About, let's see, which release was this? I don't have it handy, but the other session on galaxies that we've already had. All of the webcast videos from previous sessions are already online, as well as all of the materials, the presentations, and the press releases from the previous press conferences. They're all in the press kit on the AAS website. So just a reminder that we are recording this and we're streaming it live to YouTube. The way this is going to work is I'll give a brief introduction to the topic and I'll introduce our speakers for the day. Oh, and I should mention that we also have an astrobider with us monitoring the press conference today, Sanjana Curtis. She is the Astrobytes media intern for this meeting. So I'll introduce the panelists and then each of the panelists will give their presentations. We'll go back to back in order. And then at the end of their presentations, we'll move to the Q&A session. If you would like to ask questions, you can do so at any time using the Q&A feature at the bottom of your screen. You can type them into there. When you ask a question, please include your affiliation and who the question is directed to. And we'll be keeping track of those as we go. And at the end of the session, I believe Rick will be monitoring the Q&A and he will go ahead and read those questions to our panelists when we move to the Q&A session. And the panelists will answer them live. Note that because this is using this Q&A feature, you can also go through and read all of the questions that other folks have asked, and you can upvote them. If they're questions you also want to know the answer to, you can comment on them. So please feel free to do that. So our topic for today is mysteries of the Milky Way. Yesterday, was it yesterday? It all blurs together. Yes, yesterday, we had Galactic Center to and fro. So we looked at the center of our galaxy and we've talked a bit about the Fermi bubbles and the circumgalactic medium. So now we're going to move away from the center of the galaxy and look further at the circumgalactic medium and the broader picture of things. So our panelists today, we're opening with Dhanesh Krishna Rao, who's from the University of Wisconsin-Madison. He's going to be giving a briefing titled First Optical Measurements of the Fermi Bubbles Probe Their Origin. Next up, we'll have Smita Mathur from Ohio State University. She'll be presenting on the hot circumgalactic medium of the Milky Way. Then Angie Gupta from Columbus State Community College will present how ubiquitous is the hot component of our galaxy's circumgalactic medium. And finally, Robert Benjamin from the University of Wisconsin-Whitewater will present discovery of a thin circular 30-degree ultraviolet arc around the Big Dipper. So I'm going to go ahead now and let Robert set up for, sorry, not Robert, Dhanesh set up for his presentation. Go ahead and unmute your mic, great. And the rest of us will turn off our video and mute our mics.
Okay, hi everyone. I hope you can all see my screen now. Is that working fine?
Yes.
Okay, perfect. So I am Dhanesh Krishnarao, or DK. I'm currently a graduate student at the University of Wisconsin-Madison, and I'm really excited to present some work we've done on our first discovery of optical light coming from the Fermi bubbles, which is going to help us probe the origin of the Fermi bubbles. So you can read a little bit more about this work. The paper was posted on the archive yesterday. This is work I've done with both Bob Benjamin, who's actually also on this panel, but for a different release, and also Matt Hafner. Okay, so you hopefully have heard a little bit about the Fermi bubbles yesterday if you tuned into the session there where Andrew Fox talked a little bit about them. I will give a brief introduction on the Fermi bubbles by going through this video from a NASA press release of the initial discovery. So this is showing how the Fermi bubbles were first discovered using the Fermi Space Telescope that was looking at gamma rays. And after a lot of processing of the image, you can start to see these lobes emerging. And now we're showing an artistic conception of what we think this structure actually looks like in 3 dimensions. So we believe these massive lobes, bubbles, are expanding out from the center of our galaxy. So here again is the full sky Fermi gamma ray map. After you do all of this post-processing to account for what's closer to us, what's farther away in the background, we start to see the bubbles emerge. So that 2D image is what lets us inform and create these 3D models to explain what we think is this Fermi bubbles. So these Fermi bubbles are our best 3D models that are based on this initial 2D image that discovered them. They place these bubbles to be huge structures centered at the very center of our galaxy, extending almost 50,000 light years above and below our galaxy. So what these 3D models and interpretations allow us to do are make really big predictions about what these bubbles are like, how they're distributed in our galaxy, and what kind of an effect they have on its environment. So our best current 3D models that are all based on these 2D images really describe it as a growing relic of a powerful outflow of gas from a long time ago. And so one of the benefits of the fact that we think it's an outflow of gas is that we can actually use the fact that we think this gas is moving outwards in this cone shape, combined with the Doppler effect to measure slight shifts in the wavelengths of light coming from this structure. So if gas is moving slightly towards us, where in this picture, the sun is approximately at this location, if gas from this structure is moving outwards in a cone, then gas in this side is moving slightly towards us and would be a little blue shifted, while gas on the farther side is moving slightly away from us in this cone shape. So it'll be red shifted. So these 3D models can make these predictions on exactly what kind of changes in this velocity that we can expect if we're able to measure it. And some of these first measurements came in 2015, where Andrew Fox and others used the Hubble Space Telescope to look at ultraviolet light from a very distant source. So these are looking at distant, bright quasars from other galaxies that are actually between us and the Fermi bubbles are between these bright, distant sources and us. So by looking at the bright light and measuring how much light passes through the structures at different colors, we can actually see that some light is missing in the slightly bluer direction over here and the slightly red direction over here. And that tells us that we're seeing gas that's being absorbed, absorption lines in a spectrum. That gives us a measurement of both how much ionized gas there is and also the velocity of the gas. So this is one of the first times that we were able to add that third dimension in the form of velocity to a 2D picture of the Fermi bubbles and be able to say how fast the gas that's escaping from the center of the galaxy was going and measure the expansion of these bubbles. One downside of this technique, though, is that while very powerful, you have to have this kind of distant, bright background source in order to look for this change of light as it passes through the medium. So what we're excited to tell you about today is our latest discovery of emission of light coming from within the bubble itself. So using the Wisconsin H-alpha mapper, or WAM, we've discovered emission at visible wavelengths of light coming from ionized hydrogen gas. That's at the exact same blue shifted velocity as where you see that ultraviolet absorption from the Hubble Space Telescope. So the combination of this emission of light coming from the bubble itself and the absorption that you see of light that passes through the bubble at the same velocity allows us to make really direct measurements of the density, the pressure, and other conditions of what's happening in the gas within these bubbles and these structures. And like I mentioned, since instead of the ultraviolet requiring these distant bright background sources that are pretty sparsely located in the background, when looking at the visible light emitting from the bubble itself, we can actually follow the bubble in 3D space and make continuous maps of what this 3D structure looks like in visible light. So real quick, the Wisconsin H-alpha mapper, the telescope that we use to make this discovery, is very key to our work. It is the most sensitive telescope of its kind in the world and funded by the National Science Foundation. And it observes a telltale red glow that comes from ionized hydrogen throughout the Milky Way. So what's being shown here is from previous work with the Wisconsin H-alpha mapper, a survey of the entire sky in this H-alpha light from ionized hydrogen. And it's just stepping through different directions of the sky. And you can see how there's puffy, glowing gas, essentially in every direction of the sky that we look, that comes from this ionized hydrogen. And in this work, we're just focusing on one direction that passes through these Fermi bubbles. So just to summarize, the main findings of our initial results here are that by measuring the optical emission that's associated with the Fermi bubbles and combining it with the power of the previously found ultraviolet absorption, we're finding that the gas associated with this structure has a very high density compared to what we would expect for gas at the same height above the sun's location. Additionally, the pressure that the gas is experiencing here is about 100 times higher than what we would expect by the sun. And it seems to be pretty consistent with the existing models of what would happen in this kind of outflow from a galactic center Fermi bubble model. In the future, which is where the real power of this discovery lies, is that WHAM can start to make the first ever 3D maps of the Fermi bubble, where that third dimension is velocity. So we can look how the structure is changing spatially and in terms of how fast the gas is moving, and really nail down the models and test the predictions made by pre-existing models and create new models to better understand what the structure is like in 3 dimensions and what their origin is, what caused these bubbles to be emitted as a function of time. And so you can read more about this on the archive, and feel free to contact me by email. You can find me on Twitter as well. And you can also find some information about this on my website, which is a great domain name from Denmark, www.astronomy.dk. Thanks.
Can you please stop sharing? Hello, everybody. Can you hear me?
We can.
Great. My name is Smita Mathur. I'm from the Ohio State University, and I'm going to talk to you today about the hot circumgalactic medium of the Milky Way. I know you have attended previous press briefings, and you might have heard my graduate student, Sanskriti Das, talk about it, but I am going to give you a little bit of background and talk about our new discoveries concentrated on the Milky Way. We use a range of multi-wavelength observations to study the circumgalactic medium of our galaxy and other galaxies, but for my focus today is going to be on observations with NASA's Chandra X-ray Observatory and ESA's XMM Newton Observatory. So what is really the circumgalactic medium? Our view of the universe traditionally is optical centric. So when we think about a galaxy, we think about the tiny stellar disk which is beautiful spiral arm structure for our Milky Way. That's what we think about. Maybe we can even think about the Magellanic clouds that we can see from the southern hemisphere. But this stellar disk of the galaxy is actually sitting in a huge dark matter halo. And what theoretical models actually tell us that this large dark matter halo, which actually contains a volume 1,000 times that of the disk of the stellar disk of the galaxy, should also be filled with gas. And this gaseous medium is what is called the circumgalactic medium, though I would actually prefer to call it intragalactic medium, because galaxy actually is defined by the entire dark matter halo. So this is what theoretical models have predicted, that the circumgalactic medium mostly is at warm, hot temperatures of about 1,000,000 Kelvin. The theory also told us that the circumgalactic medium contains most of the meteoric mass of the galaxy, at least as much of the entire stellar disk, but most likely more. And this circumgalactic medium also likely accounts for the missing baryons in galaxy that are expected to be there based on the mass of the dark matter in the halo. So understanding this circumgalactic medium is therefore a very important thing to understand the galaxy itself, and in the context of formation of the galaxy and the evolution of galaxy, role of feedback, and host of other astrophysical questions related to that. So this is what was expected from theory, and this is what we finally achieved after more than a decade of observations with Chandra and XMM, that back in 2012, we actually established that indeed this circumgalactic medium is made of million-degree gas. The gas is very diffuse, low density. It is extended really most likely all the way up to the virial radius of the galaxy. And indeed, it is very, very massive as expected from theory. Over the next few years, we went on to characterize this circumgalactic medium to put it in the context of galaxy formation and evolution. Now I'm taking you to 2017, when we obtained an unprecedented, extremely high signal to noise spectrum with XMM Newton. We observed a background source called 1AS1553 for close to 2 megaseconds. And that led to one of the most beautiful spectra that we had seen in X-ray band. And we saw the absorption lines of nitrogen. We saw the absorption lines of oxygen that we knew ought to be there, which are the telltale signatures of the million-degree gas that we expected to be there. And we also saw neon lines, the extremely strong neon line of highly ionized neon here is actually very important. This spectrum is so beautiful that it gave us not just one or two, but three independent amazing results that nobody had thought about. The first result is the discovery of a hot component in the circumgalactic medium. In addition to the million-degree gas, we now discovered also 10 million-degree gas. We also found that the gas mixture is non-solar, that the ratio of nitrogen and neon to oxygen is not what you would expect if these ratios of these elements were similar to what we see on the sun. This was not expected either. Other thing that we found, that how strong the neon we had seen, we also should have seen strong lines of iron, which we do not see. That tells us that the origin of these elements possibly are related to supernova explosions, or are they really? So these three independent observations have now these three independent results have now told us something unique about the circumgalactic medium that no theory had ever predicted, and all theoretical models going forward must explain. We also observed emission around the same direction in which we saw the absorption, thinking that measuring the emission characteristics will help us understand exactly where this hot gas is located and what its characteristics are. But to our surprise, we actually found the following. So this is showing you what are the temperatures that we observed. Here are the two temperature components that we saw in absorption. And here are actually two components in temperature that we found in emission. The emission spectra also required two components. But to our surprise, the emission components and absorption components did not necessarily match. So we have now in the X-ray emitting region between 1 million to 10 million degrees, not just one or two, but at least three different components and maybe even four. This is a very surprising discovery. So these observations are now providing us with new insight on the chemical enrichment of the circumgalactic medium, as well as its thermal history. What makes this hot gas? How are these elemental ratios like that we see? What is the origin? Where is this gas coming from? These are the kind of questions that we need to answer, but before we answer that, we need to know whether the direction that we looked into, is it unique or is this a general property of the circumgalactic medium of the Milky Way? And for that, I would lead you to the next briefing by Angie Gupta and leave you with this nice image made for us by the ESA press office. Now it shows you the circumgalactic medium, not just one color, but three, showing the three different temperature component and all these dots representing different elements of elements present in the circumgalactic medium. Thank you.
Why it's not showing that? Okay. My name is Angie Gupta. Are you able to hear me?
We can.
Yes, okay. I am from Columbus State Community College, and I will give the follow-up on the how ubiquitous is the hot component of the Milky Way Smita just talked about. But before that, I like to tell that I will present the result of the work mostly done by my undergraduate student, Josh Kingsbury, and I would like to kudos to him for doing this wonderful work at the undergraduate level at the community college. Okay. So now I will talk about how ubiquitous is the hot component. The circumgalactic medium is an important component of a galaxy where most of outflows and the accretion happen. Therefore, it's essential to understand this component for the formation and evolution model of the galaxies. When we talk about the Milky Way galaxy, an image something like that comes into our mind, like the stellar disk with the beautiful arms where most of the star formation happen. But now it is well established that this disk is actually embedded into a very large cloud of warm hot gas. And here are our neighboring galaxies, LMC and SMC. And the temperature of this warm hot gas is about 2 million Kelvin, and it's extended to a large distance, about the 10 times the size of the stellar disk. And the mass of this warm hot gas is about more than 60 billion solar masses, which can account for most of the missing normal matter of our galaxy. Now, as just Smita mentioned, recently we found another component of this warm hot gas into the circumgalactic medium at a very high temperature reaching near 10 million Kelvin. Therefore, the important question to ask is, how ubiquitous is this hot component? Is the cycline of 1ES is unique where we have the confirmed detection of this hot component, or this hot gas is more widely spread into our galaxy? This image is showing the Rosard All-Sky survey map in the 3/4 keV X-ray image, and the white cross mark the cycline of the 1ES where we have confirmed detection of the hot component. And excited by this discovery, we searched for the similar hot gas in other 4 sightlines marked here with the yellow crosses using the Suzaku and the Chandra observations. Okay. The Suzaku was the Japan's X-ray astronomy mission, which was in the sky from 2005 to 15. It can observe the sky in a broad X-ray energy range of 0.3 to 700 keV, though we are mostly interested into the low energy range of 0.3 to 12 keV. And the Chandra is the USA's X-ray astronomy mission, which was launched in 1999 and still beautifully observing the sky into the X-rays. And it has a very good angular resolution. Whenever we look into a sky with the X-ray telescope into an empty region I mean where we don't have any bright X-ray source, like the active galactic nuclei, galaxies, or clusters of galaxies, we see this diffuse emission. And this diffuse emission is a combination of multiple sources, like the local emission from our solar neighborhood. And the warm hot gas in the Milky Way halo is a major component to this diffuse emission. And beyond that, we have extragalactic emission due to the unresolved sources known as cosmic X-ray background. And we use the Chandra and the Suzaku observation to separate these different components. Like this image is showing the diffuse emission spectrum for one of the Suzaku field. Here, initially we tried to model it with the typical components like the local emission and the warm hot gas into the Milky Way halo. But we found like in 3 out of 4 sightlines, there is some excess emission around 0.8 to 1 keV. To model this excess emission, we needed to add another thermal component which fit this excess emission, and temperature of this thermal component is similar to the one we found into the 1ES sightline. Okay. So that means in 3 of these sightlines, along with the warm hot component, we also need another hot component to model the whole emission. And the temperature for this hotter component is about 9 million Kelvin, similar to the we recently found or discovered. Okay. So we search for the hot component towards the 4 sightlines using the Suzaku and the Chandra data. And we successfully detected the hot emission along 3 of those sightlines. And the temperature of that hot component is about 9 million Kelvin, much hotter than the known warm hot gas into the Milky Way halo. Okay. So here are my results that the recent discovery of hot component of the Milky Way halo is not unique. This means this one ES sightline is not unique. The hot component of the Milky Way halo is more ubiquitous. We have detected it successfully in the 3 sightlines, though we don't know how homogeneous or isotropic it is, or is more sparsely distributed into the galaxy. To characterize the more property of this hot gas, we need to search for the similar signature into the more sightlines. But this is exciting to see this hot component not into in the one sightline, but into the multiple sightline. Thank you.
Hi, my name is Bob Benjamin. Can you hear me and see my slides?
We can.
Okay. Well, thanks a lot. So I'm going to talk about something that's closer to home. Almost 20 years ago as a postdoc, I published a paper with a colleague, Peter McCullough, who's now at Space Telescope Science Institute, about the discovery of a 2.5-degree straight line of H alpha seen in the sky. H alpha, of course, is a red optical emission line. Peter discovered this while experimenting with an H alpha camera. And when he showed this to me, we both became fascinated to speculate on what this straight line was. The location of this straight line in the sky is shown in this night sky image, a view from Chicago at 2:20 tomorrow morning. And now, thanks to two postdocs, Andrea Bracco, who's currently working at the Rudyard Boskovic Institute in Zagreb, Croatia, and Marta Alves, formerly of Radboud University, now working in private industry, we now understand that this 2-degree line segment is actually just a small section of an ultraviolet arc. We believe that this arc is actually a shock front produced by a stellar explosion, possibly a supernova, that's centered near the handle of the Big Dipper. And the shock front crosses between the Big Dipper and in front of Polaris. If this is a supernova shock front, then this object, which we call the Ursa Major Arc, would be part of the largest angular sized supernova remnant in the sky. It covers 2,600 square degrees of the sky with an angular diameter from here to the center of 60 degrees. The distance of this object is uncertain, but we have reason to believe it's more than 600 light years away, and the explosion occurred more than 100,000 years ago. And we're seeing the shock front where our line of sight is tangent to the expanding front. It's possible that gas in the center is still heading towards us, but given our estimated distance and the shock speed, we expect that the shock front would be slowing down, and by the time it could reach the sun, it would be to normal sort of interstellar speeds. This direction of the sky is well known for having very low densities of gas and dust. It contains several windows, for instance, the Lockman window and the growth strip, that are used by extragalactic astronomers to study galaxies outside the Milky Way. Although we don't think that an explosion that would create this arc would completely clear all the gas and dust out of the way, we think that it may have contributed to the clearing of the dust and keeping this extragalactic windows open. One last thing I want to say before I show you some of the images is that although the full arc was initially found in archival data in NASA's GALEX, the Galaxy Evolution Explorer mission, we also found that a team of amateur astronomers conducting their own H alpha survey of the sky had actually imaged a section of this arc in H alpha. And when we contacted them, we found that the H alpha and the ultraviolet emission lined up pretty much perfectly. Their confirmation image, along with our ultraviolet results, were published in the April edition of Astronomy and Astrophysics Letters. And Andrea Bracco, who is the person who actually discovered the GALEX arc, is the lead author of that publication. I should mention that one of the members of the amateur astronomer team, Sean Walker, is actually present at the AAS meeting in the Sky and Telescope booth. So if you want to hear about the amateur astronomer side of this, you can talk to him. So to continue on, okay. So, oh, and I forgot to show, so this is my collaborators, Andrea, who was the one who discovered the arc, and Marta, who was the one who initiated the project. So here's the image of the arc. This is actually a mosaic of GALEX images showing a clear structure, very thin, that crosses across the sky, has an arc length of about 30 degrees. You can bring out the contrast by looking at the gradient of this image, which helps clear up the background. And you can see this beautiful arc. In some cases, it seems to split a little bit. And this is actually characteristic of the shock fronts, the very thin shock fronts of rippling shock fronts of supernovae. So again, as I mentioned, this is discovered in GALEX. We see it in both the far ultraviolet channel and the near ultraviolet channel. And we also detect it in H alpha. As I mentioned, this started off as just a 2.5 degree arc. This is actually the paper that Peter and I published in 2001. At the time, we speculated about what it might be. This was Peter's original discovery image. He re-imaged it with a different telescope to make sure it was real. And in the paper, we noted that this filament could actually produce Faraday depolarization, basically a radio astronomy effect. 20 years later, that prompted Marta to start a project looking at this object with a low frequency radio telescope, LOFAR in the Netherlands. And in order to help interpret the data, Andrea started looking at different data sets, and that's when he discovered the ultraviolet counterpart. So here's the ultraviolet image again. And the amateur astronomer team, the MDW survey, this is actually their image. So you can see that this arc, which corresponds to this irregular region here, pretty much lines up with the observed ultraviolet arc. So its basic characteristics, 30 degrees in length, multiple arclets, centered 60 degrees above the galactic plane near the handle of the Big Dipper. Its most characteristic, interesting phenomena is 30 degrees radius, 60 degrees diameter, and very, very thin, only 0.6 to 0.8%. The thickness is 0.8 to 0.6% of the radius. We actually have found some other arcs in the GALAX data, but there's nothing as clear and large scale as this. And we think that the source of ultraviolet emission is basically associated with recombination from hydrogen gas. Here's an image of another very large supernova remnant, or at least we used to think of it as large. This is actually the remnant G70-21.5, first discovered as a remnant in 2015. It has a diameter of 8 degrees, as opposed to 60 degrees for the object in question. But you can see that the comparison with the H alpha and the GALAX is very, very similar, like we see. And you can see curved shock fronts at the leading edge of the blast wave, again, like what we see. So again, if you superimpose it on an image of the sky showing the column density, or the basically total amount of hydrogen out of the galaxy, you can see that it gets dark in certain regions. These are these so-called windows that I mentioned. We have very little constraint on the distance of this object. It could be basically nearby, which would make it small and young, or it could be further away, which would make it older and larger. And so, but if we assume that this cloud, which shows evidence of hydrodynamical interaction with hot gas, is inside the bubble, that would actually make this object more than 6,000 light years away. And so that's our best constraint, but getting the distance is tricky for this structure. So the conclusions here is we have found that the 2.5 degree straight narrow filament is less straight than we thought. It's a curved shock front. It's evidence for a 60 degree diameter old supernova remnant covering nearly 1/3 of the northern sky above B of 30. This is larger in angle than the previous record holder by a factor of 3 and 4 times larger than well-known supernova remnants like the Cygnus Loop and Vela. Its age is uncertain, but we estimate approximately 100,000 years old, 60,000 light years away to the explosion center, and it may be related to a clearing of interstellar gas above the sun. This is the contact information for us. If you're interested in doing a story on this, I would highly encourage you to contact Andrea and Marta, who are the ones that made this all possible. And I just wanted to say, this is probably the only discovery I've ever been involved with that could be plotted on a state flag. So that's it. Thank you.
Great. Thank you so much to all of our speakers. Let's go ahead and all turn on our videos at this point, and we'll move into the Q&A session. I want to note that Anjali has an oral session that she needs to get to at noon. And so we'll start maybe with questions for her, but if there are any more questions for her later, Smita has offered to answer those as well. So I'll hand it over to you, Rick.
Okay, very good. So so we'll take this first question, which is for Anjali, and Smita has offered to answer it. It's from Sky and Telescope, Monica Young. What's the big picture of what we can learn by detecting this hot component? What does this mean for the evolution of our galaxy? And do we expect to see this hot component around other galaxies, or at least certain other galaxies? Anjali and Smita, you can both answer it as you wish.
Okay, so I will go ahead and Anjali jump in as you would like to. So this is a great question, and answering this question is going to keep us busy for years to come. And we are really excited to work on this, looking forward to it. But there are some ideas. So the million-degree gas in the circumgalactic medium, as I said, is expected. That's created in the formation of the galaxy, shocking heated when the galaxy forms. But the hot component is something that was not expected, and most likely it is related to feedback. Feedback is the response from the stellar disk of the galaxy to the outer halo, to the circumgalactic medium. And there are two different kinds of feedbacks that are talked about. One is the AGN feedback, that the nucleus of a galaxy has actually outflows, and the energetics like we see from Fermi bubble, those kinds of things also affect the circumgalactic medium naturally. But also there is stellar feedback, which is come because of there are star formation and supernova remnants and the energy coming out from all over different disks. So those are the two different kinds of feedback, and there are some other ideas I will not detail into. So these got to be responsible for this very hot gas that we are seeing. And therefore we were wondering that the sightline that I talked about is close to the top of the Fermi bubble. And we wonder whether it is therefore maybe unique. But as we see, as from Anjali's work that she talked about, that it is not unique, and therefore more likely that the star formation driven feedback is responsible. But this is the kind of question that, as I said, is super exciting. We're looking forward to answer. We are just at the discovery stage here. We'll try to determine how ubiquitous this hot gas is, its what we call covering factor, what fraction of the sky that it covers, and then come to general models to understand this hot component.
Yes. I would just like to add, detecting this hot gas into the multiple sight line, really confirming this has a big role to play into our evaluation and giving the feedback to our galaxy. And recently, like this Sanskriti presented in the June 1st, like we find the warm hot gas first time into the Milky Way type galaxies. So we start seeing these warm hot gas, and so we are expecting in the other galaxies also, we will be able to detect this hot component. So, thank you.
Is that because these galaxies are still forming stars? Is that the connection?
Yeah.
Correct.
Yeah.
Yeah.
Okay, great. All right. I actually, I'm going to jump in with a question myself because it's also for Anjali, and I know she's got to scoot out. Are you and Smita, are you surprised that this very hot component seems to be mixed in with the warmer component as opposed to any kind of radial distribution of temperature around the galaxy? Does that argue again for this stellar feedback because it can be more localized?
That's again a great question. So right now we do not know exactly the location of this hot component. That is very hard to know when we are seeing the emission from it. So we don't know how far it is from us, and consequently, we don't know how exactly far it is from the center of the galaxy. So answering that question is also something that we will be working on. But having seen that in these multiple sightlines now is definitely more suggestive that it has to do with stellar feedback, and whether it is we are seeing some kind of a temperature gradient, or is it all mixed in with some pockets of hot things in the middle of the more diffuse, more homogeneous warm hot component. We do not know yet.
Okay, great, thank you. All right, so the next question is for DK. It comes from Leo Enright, who's with Irish Television. First, he comments that he's in awe of DK's astronomy.dk domain name. Yes, I must admit, when I first saw that, I thought that was terrific. You're very fortunate. His question, is it realistic to look for Fermi bubbles in other galaxies?
Okay, hi Leo, thank you for asking this question. So you're wondering if it's realistic to look for these kind of Fermi bubbles in other galaxies. In general, people do see similar signatures for what we see about the Fermi bubbles in other galaxies. So they see these like large bubble-shaped, cone-shaped lobes that are kind of centered around galaxies that we look at. The people have also seen like visible light signatures moving at these high velocities emerging from the centers of galaxies. So that's a similar way that we can try and look for these in other galaxies. The real power of looking at the Fermi bubbles in the Milky Way, though, is that we can see it at really high detail. So we'll never be able to really make maps at a reasonable resolution or scale when we're looking at other galaxies. So that's where the power of looking at the Fermi bubbles so close to us really comes in.
All right, a couple more questions for you. These are from Emily Conover from Science News, I believe. Does this result tell us anything new about how the bubbles formed? And you observed the emission from the ionized hydrogen gas flowing toward us, but not away from us, correct? Why one, but not the other?
Okay, so I'll start with the velocity related question. So we're only observing the gas that's moving towards us, which by the way is moving at about 220 kilometers per second towards us. We're only seeing that as opposed to the gas that's moving away from us, that's slightly redshifted for a few different reasons. One is kind of intrinsic to the Fermi bubbles itself and where we are in the galaxy. So the gas that's moving towards us is much closer to us in the galaxy than the gas that's moving away from us. So that gas is moving away from us has to pass through more material that's between us and that gas from the Fermi bubbles. So it has a larger chance of being blocked out and obscured by dust that's in the way. Another reason is actually just kind of intrinsic to the telescope and much closer to home. So WAM is really the only telescope that's able to see this really, really faint red colored glow that's associated with this invisible light that we're observing. Unfortunately, at the positive, at that red shifted velocity, there's also a bright feature in our atmosphere that glows at the same color. So that really hinders our ability to make that measurement there at this currently. So in the future, we might be able to dig a little bit deeper and look for that, but currently we're kind of limited by our atmosphere, actually. Okay. As for if the result tells us anything about how the Fermi bubble formed, it definitely will in the future. So our measurements of these overpressure densities and pressures are in relative agreement with some existing models that go to try and explain how these Fermi bubbles formed, trying to investigate whether they come from a black hole accretion event or bursts of stars forming near the center of our galaxy. You can't necessarily rule any of those out currently with our like single detection. But in the future, when we're able to make these 3D maps of the Fermi bubbles, we can actually measure how the energy requirements to power these Fermi bubbles change as a function of position. And really what that can tell us is how over time the energy output from the Fermi bubbles has changed. So that'll really be able to nail down more about the origin of the Fermi bubbles in the future.
Okay, very good, thank you. So the next question, back to Leo Enright from Irish TV, is for Robert Benjamin. You mentioned LOFAR. Has it seen this feature?
The answer to that is probably. This whole discovery came out of the attempt to look for it in low frequency radio, and the data initially that was taken by Marta was sort of ambiguous and difficult to interpret. But with some work, there is some evidence that there is a signature in the low frequency radio emission of this object. However, the knowing about the sharpness of this front helps to define the geometry that you can use in the analysis of LOFAR data much better. And so the LOFAR data and the analysis of it is basically being revisited now that we know about the ultraviolet structure.
Okay, thank you. I actually have a question for you too, Robert. I think I heard you say that your best guesstimate for the distance presently is about 6,000 light years. But when you then showed us a summary of the characteristics, I think your slide said 600.
No, I meant 600. Yes, 600.
You meant 600. Okay. To make it even more confusing for me, when you pointed at the 600 on your slide, I heard you say 60,000. So it was 600. Just wanted to clarify the distance.
If I did that, I'm sorry. The distance that we estimate is approximately 600 light years, but it's very uncertain because of there's until we can detect this in the expanding shell in the spectra of a bunch of stars, we won't have a good constraint on the distance.
If it were to turn out to be that close, would that make it the closest supernova that we're aware of? Or, I don't happen to know off the top of my head the distances to some of the other remnants.
My understanding
Sounds close,
is the thing that's probably the closest. You know, when they get close, they get very large on the sky. And I gave a list of 3 comparable objects. All 3 of those aren't found in the standard list of supernova remnants because they're so big that it's a little hard to know for certain. But if I remember right, the Antlia remnant is thought to be the supernova remnant is thought to be the closest.
Okay.
This would be a little further away than that. I think the Antlia remnant is only about 200 parsecs away. But again, the distance to that is also very uncertain.
Mhm.
I actually wanted to follow up on that, if that's okay.
Go ahead, Susanna.
I'm surprised to see how well it traces out the spherical shape. It seems like, you know, if there's any sort of medium in the way, it shouldn't have this lovely arc.
Mhm.
So does that tell us anything about, you know, for instance, the fact that it's closer? If it had been propagating further, then I would expect it to be more disrupted.
Well, this is one of the reasons why I said that I mean, like I said, in that direction of the sky, it's well known there's not a lot of gas and dust. It's been cleared out by some mechanism. That structure is called the local interstellar chimney. And so what we think is that in the direction that we see it, the shock front has propagated through a sort of previously cleared medium. And that's why it's been able to maintain its coherency. Whereas possibly in other directions, I mean, one question is, given the fact that we started at 2 and we're now at 30 degrees, could it be longer? There, the problem is figuring out how to subtract the signal out of the galaxy background. So it could be longer than 30 degrees. But it could be that in other directions, the shock front has encountered more clouds or propagated into a low density regime where we can no longer detect the shell.
Okay, thanks.
All right, well, it doesn't appear that we have any more questions. I actually, looking back at my notes, I had one more question for Dhanesh. You mentioned the density of the gas, and you talked about comparing it to models and things. Does any of the observational data that you have now enlighten us at all on when these bubbles might have been ejected?
So our current observations don't necessarily tell us that so far. At least the work we've done with it hasn't. It will be powerful in really constraining the time, though, in the future. So older studies that have tried to tell us when the bubbles were flaring, when this alpha originated, have actually used WAM data, but from much farther away from the Magellanic Stream. So that's similar to some of the results that were described yesterday by Andrew Fox, but older than that, looking at just H alpha light. So by looking at that same light much closer to the center of the galaxy, we'll get an idea of like what's happening more recently or almost present day in a sense towards galactic center. So by comparing the differences there, we'll be able to say it happened between this time and no sooner than this, no later than this kind of time.
Okay, it's really something because I mean, the discovery of the Fermi bubbles is less than a decade old now, and we're starting to really get, well, not only confirmation that they're real, but a lot of really detailed information about them. It's pretty fascinating. All right, well, I do not see any more questions, so I'll turn it back over to you, Susanna.
Great. Well, I just want to thank all of our speakers one more time. And thanks to the PIOs who helped with the press releases and the briefing prep. And thanks to all of the members of the audience who are here. The next and final briefing of the meeting will be at 3 p.m. this afternoon. Rick will be hosting that again, and the topic is sweet and sour on satellites, and that's in all senses of the word satellite. So we hope to see all of you there, and enjoy the rest of the meeting.
Thank you. Bye-bye. Nice meeting you all, and thanks for inviting us.
You're very welcome.
Absolutely. Thank you.
Thanks to everybody.